Okay, it's 6 p.m. for me, so let's start. Welcome to the second regular session of CPP. The title of the session is Logic, Set Theory, and Category Theory. And we have exactly 3 talks with these buzzwords. So we'll start by a talk by Olivier Laurent on implementing logic with binders in COC, and then a talk by Dominic Kirst on the continuum hypothesis in set theory and in type theory, and then a talk by Jason Hu on category theory in Agda. And we'll start with Olivier. The title of the talk is an anti-locally-nameless approach to formalizing quantifiers, and it's pre-recorded, and we can start now.
This talk is about the formalization of quantifiers in proof assistance. In particular, we would like to be able to build libraries about proof theory, in particular for logics which rely on quantifiers, so that people who usually use paper for writing their proof theory result could move to machine for the formalization. Because of this goal, and since we would like to have the largest possible audience, we do not want to rely on some specific methodological construct. For the similar reason, we would like to use names rather than indices. And to make this reasonable, we need to avoid using renamings, otherwise the formalization becomes really tedious to use. Let's have a look at formulas. The usual representation of formulas with names is the following. You have a set of variables, first order terms, and then formulas. And in this talk, we will focus on the for-all quantifier. There is no difference for there exists. Trouble comes with substitution, because in this named setting, substitution may generate captures. And the only way to avoid it is to do some renaming. There is a non-solution to this problem, which is called the locally named representation. The idea, coming back from Genzen, is to introduce a new set of objects called parameters, so that terms are built from variables, function symbol, and also these parameters, which could be understood as a set of constant symbols. This way, closed terms are defined to be terms with no variable, but without any constraints on parameters. The notion of formula is not modified, but it is very important to notice that only variables are quantified. So there is no binding construct with respect to parameters. This means that when you define substitution, if you assume the substituting term to be closed, there is no possibility for capture. And you can define a simple notion of substitution, which is meaningful as soon as this hypothesis is satisfied. This is very good for formulas. Let's have a look at proofs now. We continue with Genzen ideas, and we get, for natural deduction, for example, the following rules. The for-all elimination rule has this closeness assumption because we need to do a substitution. For the for-all introduction rule, if we read it bottom-up, we open a for-all quantifier. It creates a free occurrence of x in A, and we immediately substitute it with a parameter E called the eigenvariable. There is a side condition that this eigenvariable must be fresh, that is, E does not occur in gamma and A. From this, we can consider proof transformation. If you study normalization of natural deduction, you have to eliminate this pattern of a for-all introduction rule followed by a for-all elimination. And for this, you need to consider a notion of substitution on proofs, where a term is substituted for an eigenvariable. This means that these parameters, eigenvariables, are not constant symbols anymore since they are used for substitutions. And this gives you some troubles. If you consider this example, you have a perfectly good application of the for-all introduction rule, but after substitution, the eigenvariable now appears in the context, and this is not valid anymore. So the only way to correct it is to rename the eigenvariables when you do a substitution. And remember, we would like to avoid renamings. What happens is that this for all introduction rule is a kind of conversion from the for all connective, which is binding the variable x, to the for all introduction rule, which is now binding the eigenvariable e inside the proof above. And this is this fact that for all introduction rules act as binder for eigenvariables that makes substitution difficult to enter. There is a completely different approach, which is the De Bruijn approach. It is based on defining terms with variables represented by natural numbers. As a consequence, the for all quantifier is assumed to always act on 0. The notion of substitution is usually obtained through parallel substitution, where you use a substitution function that acts on all natural numbers at the same time. You can define the substitution for a term in the formula. When you reach a variable, you simply apply the function. And when you want to apply a substitution to a for all formula, you need to lift up the substitution to avoid any conflict between the 0 in A bound by for all and what happens in the substitution. The rules as defined following this idea of parallel substitution. For the for all elimination rule, you generate a substitution function t tilde from the term t you want to substitute. And in the for all introduction rule, you open the for all on the right-hand side. But since now 0 is free in A, you need to shift up all variables in X, in gamma, sorry. And this replaces the freshness side condition of Genzel. With this notion of rules, it's reasonably easy to define a notion of substitution for proofs, which requires some lifting operations as well. All this works perfectly well, but it's really dedicated to machine because it works with natural numbers. You have a lot of indices manipulation to do, and the formulas and proof you get are not so readable for human. So what we would like to know is to take the best of the two approaches, locally named and De Bruijn, and that's what we call anti-locally-nameless. The starting idea is to rely on the notion of locally named formula. But now we choose the set of parameters to be natural numbers. This means that free variables will be natural numbers and bound variables will be named. This is exactly the converse to what happens in the locally nameless formalization. This is why we call this anti-locally nameless. Since we have two kinds of subjects, variables and indices, we need two notions of substitution. This parallel substitution for indices is not exactly the same as De Bruijn, since now when we apply a substitution to a for all quantifier, since for all applies to a variable and R acts on natural numbers, there is no conflict and we can do a simple commutation. There is no need for lifting in R. Concerning the rules, the for all elimination rule is exactly Genzel's rule. And the key novelty is in the for all introduction rule, which is a mix of the De Bruijn rule and the Genzel rule. On the left-hand side, we have this shifting operation from De Bruijn. And on the right-hand side, you have this x, which is replaced by a fresh eigenvariable, and it will always be 0 in this formalization. But since we introduce a 0, we need to shift indices in A to avoid conflict with 0 in A. So what happens is that we shift all formulas, and then we substitute 0 for x. Concerning substitution in proofs, it works exactly as in the De Bruijn approach. Let's look at an example. So these are three representations of the same proof. In these two cases, locally named and anti-locally nameless, closed formulas are represented with name, which helps a lot in readability comparing to this De Bruijn representation. In particular, the choice here of having the same name x on both sides is meaningful, while here they happen to have different number representation. It's important to notice that even if I've chosen to put in red all the occurrence here of the same variable, the associated representation varies inside the proof. In the locally named representation, we instantiate y with a fresh eigenvariable, and then it doesn't change anymore. But in the de Bruijn representation or in the anti-locally-nameless representation, the indices are changed because there is some lifting inside the proof. However, it is important to remark that in the anti-locally-nameless representation, the representation of an occurrence of a variable is the same inside the sequence. While here in de Bruijn, inside the sequence, the red variable can be both 1 and 2 at different places because of this quantifier here. This is important in practice because when you work on a proof assistant, very often you focus on a current state of a proof that is a sequence. And this uniformity of representation helps a lot for reading what you're doing at the time. To conclude, it is also possible to consider second-order quantification, but not first-order and second-order at the same time because you have additional binding troubles. And you can do various other logics and logical systems. We have been able to use names in the formalization with almost no renaming and keeping an homogeneous representation of variables inside sequence, even if in proof they may vary. With respect to our starting goal of using names, we are still using some de Bruijn representation since they appear to be the best thing to do because of this difficult binding constraint coming from the forward introduction rules. Thank you for your attention.
Okay. Thank you. We can now take questions for the talk. So you can ask the questions either here live or via the Clouder chat, or if you're watching via YouTube, in the YouTube chat. Dominic is raising his hand. Dominic, you can ask your question.
Okay, so thanks for this nice talk. I in particular enjoyed the long version of your talk. It's really instructive. What I was wondering is that if you use the normal de Bruijn rules, to me it feels more helpful to use a rule for all introduction where you do not introduce the shifts, but you can also deduce another rule which is more Gensen style with a free variable kind of simulating the parameter approach. And I was wondering if in your anti-locally-nameless version, such a rule would also be derivable where you don't have the shifts, and how close this would then be to a normal Gensen style system.
So I'm not sure I see exactly what you mean. So it's in this rule, what you do instead of shifting?
So if you assume this rule, you can also derive another rule which looks more traditional in saying that if you have a free variable x and you can prove under gamma without the shift that a of x holds, then you can generalize to the universal quantifiers. And if you do a concrete deduction where gamma might contain a lot of hypotheses, I found it easier to use this rule instead of the one introducing shifts. And I would be interested if such a rule could be still derived in your system, or if there's something kind of making it harder to derive such a rule.
I would say it should be possible, but I don't want to be too affirmative here because I've not tried this, but I don't see any key difference from that point of view with pure de Bruijn.
Okay.
Then we have a question by Andre.
All right, a very nice talk. Thank you very much. A very interesting approach. I have a question about the identity of terms. So in your approach, names matter, right? So your data type of terms is isomorphic to data type of concrete terms, not to that of concrete terms modulo alpha equivalents, if I understand. So what are the consequences of this in terms of reasoning at the proper level of abstraction?
So that's something I addressed, in fact, in the long version of the talk very quickly. And so the point is that since we are only considering deduction, considering alpha equivalent formulas to be different doesn't seem to be a trouble at all. And this means that, okay, when you put names, and names matter. And what makes things work is that clearly alpha equivalents will be included in deduction. So if you have A and B alpha equivalents, then from A you deduce B, from B you deduce A. But then when you go through proofs and all meta theory, I think it doesn't matter at all. And having a finer notion of identity of formulas is maybe be good, because it means that you can put information in names if you want.
Exactly, and there are advantages, right, in working with concrete terms. You can more easily define things by recursion. So this is a major advantage. All right, thank you.
All right, we have to move to the next talk. There is a question by Andrew in the chat, which can maybe be answered in the breakout session. So everybody who's interested in more discussion, you can move to the breakout session on Olivier's talk. And then next up is Dominic Kirst. Dominic is giving his talk live. So I invite everybody to turn on the camera to create an even more we're in the same room feeling. And Dominic's talk is called The Generalized Continuum Hypothesis Implies the Axiom of Choice in Coq, and it's joint work with Felix Rech. Dominic, you have the floor.
Okay, thank you for introducing me. So as Yannick said, this is concerned with an implication in normally set theoretic terms, and it's a result which is attributed to Sierpinski, who proved it first. And in this short talk I'm now going to give, which is basically the beginning of the long talk you also find online, I will quickly run you through the statement itself, give you an overview of the proof idea, and I will look at, in more general terms, how such set theoretic results can be approached in a proof assistant like Coq. So let me start with the statement. We have to clarify the ingredients. What is the generalized continuum hypothesis? Well, this is a set theoretic principle stating that in between an infinite set and its power set, there is no room for other cardinalities. So more formally, if you have a set X, which admits an injection from the natural numbers, so by this X is infinite, and you also have another set Y, which is squeezed in between X and X's power set, then these injections here cannot be strict. So either Y must be below X, or the power set of X must be below Y. And also Sierpinski's theorem states that this implies the axiom of choice. There's of course a lot of equivalent formulations, and we picked the one stating that every total relation contains the graph of a function. So formally, if you have a binary relation and it's total, then there exists a function that is contained in the relation. All right, so how would one prove such a theorem? If you look at the standard literature, normally you don't prove from GCH the axiom of choice directly, but instead you prove the equivalent well-ordering theorem, which states that every set can be well-ordered. And then this is further simplified by the fact that if you want to well-order a set, it suffices to well-order a larger set, because well-orders transport back along injections. So in particular, you don't have to look at finite sets, because every set can be embedded into an infinite set. And so all we have to prove is that assuming GCH, it is possible to well-order all infinite sets. And this can be done in two steps. The first step will be a central construction called the Hartogs number of a set X, which is a set that is always well-ordered, and it is large in the sense that it cannot be injected anymore into X, but it's only large in a controlled way. Namely, it is bounded by the k-fold iteration of the power set of X, where k depends on the construction of the Hartogs number we use. And with this first step in place, in the second step, you just use GCH k times to squeeze in the Hartogs number of X, and to finally obtain that X embeds indeed into its Hartogs number, and by this it can be well ordered, and we're done. Okay, so that's the idea. If you want to mechanize such a theorem, of course, you have to clarify what formal notions are involved. And as we have seen in the proof sketch, there's not so much involved. And in particular, all these notions are pretty abstract. And this means that using an expressive proof theory, like Coq's type theory, we have two strategies how we can tackle such a result. There's one strategy, which is the conservative approach of axiomatizing some variant of set theory and then proving Sierpinski's theorem in this axiomatization. But there's also the second approach, where you use Coq's type theory itself to represent all the necessary notions and then formulate Sierpinski's theorem for Coq's type theory. And we have done both. And why have we done both? Because first, if you want to mechanize axiomatic set theory in proof assistance, there's a lot of design space, and we propose one variant which is really convenient to work with, in particular in Cox type theory. And the second one is interesting for itself because it tells you something about type theory. It's a result transported from another foundation of mathematics into type theory, and it tells something about the connectedness of different foundations on a high level. Okay, in the remainder of the talk, I now want to quickly dive into both of these approaches, so you have an idea of how it feels. Mechanizing set theory in COC would probably start semantically, so you would start off axiomatizing some model in the form of a type of sets, which is enriched with a lot of structure, for instance, expressible to give you set operations that are guaranteed in the Semi-algebraic axiomatization. And then at some point you reach a decision, namely in Semi-algebraic set theory, there's this replacement axiom which guarantees the existence of sets obtained by mapping a functional relation on a given set. And in first order set theory, this is normally formulated as an axiom scheme where the functional relation is expressed by a first order formula in two variables. And we have seen in the talk before that mechanizing first order logic is not really trivial, and also it's just some additional work that we might not want to do at this point because we just want to write down what the replacement axiom is. And then the way out offered by a higher order logic is that you just quantify over all functional relations that are definable, and you don't just look at the first order definable ones. And by this you have a stronger version of the replacement axiom available, which is easier to work with because first it's easy to formulate it. You just have to quantify over all binary relations, and then you can also instantiate it easily because it suffices to write down a particular relation on type level, and you don't have to show that this can be encoded as a first order formula. And by taking the higher order view on set theory, you can actually also streamline a few other axioms, and by this obtain an axiomatization that has been proposed in a previous paper. Okay, that's the set theoretic view. So let's look at the type theoretic version. So first, it is of course well known that a lot of very abstract set theoretic results do apply to type theory. For instance, the equivalence of the well-ordering theorem and the axiom of choice. And in particular to Cox type theory, you can say that this is somewhat close to set theory because you have this impredicative universe of propositions available. And with this universe, there's a direct representation of power sets, namely as unary predicates. And moreover, by this induced, you have a notion of anonymous propositional existence that can be used to hide away the witness of existential proofs. For instance, this is used in the notion of cardinality comparisons relevant for Sierpinski's theorem, where we use the existence of injective functions, where the existence here now hides away the concrete function showing the cardinality comparison. Moreover, this type theory can express a variant of unique choice, and unique choice is of course somewhat hardwired in set theory. And since this axiom is consistent in the type theory, you can just assume it for ease, and then your setting is directly a bit closer to set theoretic arguing. All right, so how would a statement like Sierpinski's theorem look like in type theory? We just have to explain how GCH and AC look like. And for GCH, we just have to clarify what we quantify over and what the power set now is. And unsurprisingly, we can quantify over all types. And as said before, the power set is the type of unary predicates. And turning to the axiom of choice, we have to clarify what relations and functions are. And here we can just use the type theoretic notions of those. And in particular, it's now important that here we have this propositional existence, because otherwise the statement here would be trivial. All right, so the situation can be summarized as this. There are three levels of set theory present in type theory. There is the conservative first order level available, where you have axiomatized type of sets and then first order encodings of all abstract notions. But those abstract notions all exist on a type theoretic level directly. And in between these two worlds, as a bridge, you have higher order set theory where both of these notions coincide. And so you can rephrase Quine and say that higher order set theory is actually type theory in sheep's clothing. Okay, so let me end with this slide summarizing what we have concretely done in our paper. So we are not the first to mechanize Sierpinski's theorem at all. This has been done already by Mario Carneiro in MetaMath, taking the first order view. And what we have done now in COC is taking the two views that I have sketched in the previous minutes. So we do a mechanization in higher order set F, which still gives the argument in a set theoretic way with notions available like ordinals. And then we adapt it to a purely type theoretic version of Sierpinski's theorem, first with also assuming unique choice, and then we actually show that this further assumption is not so necessary. And overall, we found that COC as a proof assistant is well suited for this because first on the theoretical level, it gives you a lot of axiomatic freedom. So for instance, you can just assume classical logic, which of course is necessary when mechanizing set theory, but also as a system, it's mature, so it offers you all these helpful features that we have used in our development that made the development pretty compact. And I want to end with showing you this link where you can find the paper preprint, the COC documentation, the COC files. And you can, of course, also have a look at the full talk where I would now continue explaining the proof in a more detailed way in both of the settings. And here I will stop now. So thanks for your attention, and I'm happy to take questions.
Thank you, Dominic. So you can ask questions in the chat or raise your hand. Maybe for everybody it's interesting. Normally, Dominic is sitting right across the table from me in normal years because we're sharing an office. So for me, it was very nice to hear him talk about interesting things again in this office, because for a year we couldn't both go. Okay, there's one question by Andre. Andre?
I think there was another question by Jesper.
Yeah,
there's a question.
I can also ask it like, so I was wondering, like, you're using two different approaches, either the embedded set theory or the type theory directly to prove a result. But this also means that the end result that you prove has a different formulation. So are these two end results, are they equivalent, or is one more powerful than the other?
So if you just assume a model of set theory, then this will be weaker than the full result you have on type theory.
Right.
Because this just talks about a certain extent of the type theoretic hierarchy, and you don't know how big your model actually is. And the general theorem is really disconnected because both in the premise and in the conclusion, you quantify over either the types or the sets. And so you cannot directly derive a connection. But indeed, both of these proofs are somewhat local. So you just need a few instances of GCH to derive AC given a particular set or type. And by this locality, you can really, I haven't done this, but it should work in our formulation. From the type theoretic version, you can derive the set theoretic version. And the other way around, this will not work because here, as I said, it's not clear that every type can be actually encoded inside of the model you assume.
Okay, that's very interesting. Thanks.
All right. Now we still have time for the question by Andre.
All right, thanks. Thank you for the very interesting talk. So it's really nice to see formalizing set theory in type theory. So I have a question about your first variant. So this really is not first order Zermelo-Fraenkel theory, if I understand correctly, but let's say the second order theory that arises from modifying the separation axiom with a second order flavor. Which is in a way a different result, right? You take advantage of more expressiveness. I'm wondering if you can capture some of this, well, actually the whole first order situation, avoiding syntax altogether, but defining inductively what it means to be a first order definable set, and then basically have a variant of this result that applies to genuine first order Zermelo-Fraenkel set theory.
And that would indeed be really interesting. And I have tried it several times. And so far, all my attempts, and also with other students, always ended up in using some way of representing the syntax first. So we couldn't come up with a way to make this a more first order result, which does not really do the work involved to make sure that really your replacement axiom is weak enough. So if you have concrete ideas, I'm of course very happy if you can help me out there.
Absolutely happy to chat. I cannot go in the break room right now because I'm the host, but very happy to chat afterwards. And thanks again for the interesting talk.
Everybody who can go to the break room and is interested in asking more questions should now go to the break room.
So I'll try to create, this is my first breakout room.
It's created. You
created it, thanks.
It's always the same. It's always the same, just has to be initially created.
Right, just to remind people. So there's this breakout room where you can go immediately after the talk and ask more questions to the speaker. But you can also continue with the other talks as well.
At least Dominic should go there.
And how
should go to the break room.
I didn't see a notification how I join.
You don't have to get a notification. You just hit on breakout rooms and select room 1 and join.
Okay.
Okay. Then here we'll continue by the third talk. It's pre-recorded again. It's a talk on formalizing category theory in Agda by Jason Hu and Jacques Carrette.
Hello, everyone. Welcome to our talk about formalizing category theory in Agda. To begin with, in general, why do we care about formalizing category theory in proof assistance? Well, one reason is to study category theory itself. Another reason is one might want to study the proof assistant. Some others might want to apply the formalized category theory to the study of other related fields. For these reasons, many have attempted to formalize category theory in various systems, including Agda, Koch, Isabel, Lean, Idris, and many others. In Agda, there was a previous library, and most development effort is spent on multiple Koch libraries. Here is a summary table of some previous work. As you can see, many libraries, there are many systems involved here, and indeed many libraries are in Koch. In terms of scale, in lines of code, many libraries are under 15,000 lines of code, while these two libraries, this one in Koch using homotopy type theory, and this one in Isabel, they are close to 100,000 lines of code. So given a previous library existing in Agda, why on earth do we implement yet another one? One good reason is the previous library stopped working in Agda 2.5.2, and what's worse, it used some additional constructs like Stracher's axiom K, irrelevance, and even some postulates. So in our library, we want to improve the previous library overall by adapting it to Agda 2.6 plus, limiting ourselves to multi-love type theory, reworking the module layout such that it's more user-friendly, connecting it with the standard library more tightly. We also want to provide more properties instead of just a bunch of definitions. Currently, the library has around 27,000 lines of code. It had around 24,000 lines of code at the time of submission, so it has a pretty decent growth rate. There are more than 10 contributors other than us, and compared to the previous library, which has around 12,000 lines of code, we more than twice the size. The library has lots of setoid-based category theory. By setoid-based, we mean each category carries its own notion of equivalence relation. We discuss it in the paper and the long version of this presentation. The library has most of basic definitions you would expect from a category theory library and many lemmas and theorems. It also has a decent amount of enriched and higher category theory. Just to name a few things we have in the library, we have the following concepts like category, functor, natural transformations, adjoint functors, various monoidal categories, Cartesian closed categories, comma category, initial and terminal objects, products and coproducts, ends and coends, etc. We also have many constructions, including the category of categories, the category of setoids, the category of presheaves, the category of monoidal categories, etc. We also proved a lot of properties. The classical ones include the Unida lemma, adjoint functor theorem, Lambek's lemma, right adjoint preserved limits, local Cartesian closure and Cartesian closure of the category of setoids, and many others. And this list is not exhaustive. In order to help us design a general library, we employ the following basic principles. We use setoids to model home setoids because this would allow us to follow the standard library as tightly as possible and is compatible with K turned on, which is what this option for, and cubical Agda, which is what this option for. We also employed universe polymorphism because it allows concept reuse across different universe levels. We enforce definitional duality. Duality is a principle that is frequently used in category theory. It allows us to prove only one theorem but get another one for free. So we would like to adapt this idea to all concepts in our library. So as a result, some definitions need adjustments, including we need to add some laws in the definition of certain concepts, including category, monad, and natural transformations. We also provide proofs of definitional duality in our library. You can find more details about this in our long presentation and the paper. Another principle is that we use records for encapsulation. This principle has some interplay with the feature of record modules, and this would allow us to shrink the size of the code quite drastically while even improving the readability of our library. Again, we'll discuss it in greater detail in the long version of the presentation and the paper. Sure, the library is not about just engineering Agda in particular. We also discover some aspects that is about category theory, and we want to define our version of category theory in a more type theoretic way. One observation is that we notice category theory on paper is primarily set theoretic because, for example, we use languages like small, locally small, finite, stuff like that. And these languages, they are very set theoretic. And if we want to encode it in type theory directly, it will essentially lead to a philosophical commitment of assuming types are sets. So that's not some philosophical commitment we would like to make. In order to achieve a better, more type theory friendly version of category theory, we we would like to pick some more type theoretic definitions. We also realize that there are cases where we need to talk about natural isomorphisms between the home sets, and this is a very set theoretic language. In order to not do that, we discovered a pattern to transform a certain kind of natural isomorphisms between home sets into adjunctions and mates. Another kind of set theoretic language we might use is set theoretic quantifications like finite categories. We transform this language into one that uses adjoint equivalence. Please see the long version and our paper for more details. Our library is freely available at this URL. If you want to contribute, please feel free to submit a PR. You can definitely use our library to study category theory and other related fields. We realize that there's much design space to be explored in formalized category theory. And of course, in this short talk, we cannot possibly exhaust every single aspect of our paper. So please feel free to check the long presentation and the paper for more details.
Okay, thank you. For the discussion, I see Jacques is here, but Jason is not joining us. Okay.
He told me he would be, but.
All right. We have one author here, so we can ask questions. And while you're thinking about your question, maybe Jason is arriving. I'll start by the first question. Oh no, there's a question by Andre. So Andre, you can start.
Me again. Sorry. I think the talk was very interesting. I especially found interesting this avoidance of the philosophical commitment to modeling certain notions in a set theoretic fashion. So I'm wondering, on the one hand, you managed to encode them in a type theoretic, let's say honest to goodness type theoretic fashion, but on the other hand, the set theoretic flavors are also definable in some sense in the same formalism. So I'm wondering whether they are equivalent or whether the type theoretic version is more general than the set theoretic version.
Oh, more general is quite hard to pin down. Certainly what we've discovered, because Agda has universe polymorphism, is that we certainly could be much less committed to size issues. Pretty much, we were very careful to make our definition as size polymorphic as possible. And so the system helped us choose definitions that don't force, that don't push size problems on you. And so this was really quite educational, because things like adjoint functors being defined by Hom-set isomorphism is actually not size polymorphic, whereas by unit and co-unit it is. So somehow type theory helped us find the more elegant categorical definitions that traditionally are seen as equivalent, but that's because everybody says, oh, yeah, there's size issues, don't worry about them. Well, they should. Otherwise, I think it ends up being really quite different in the sense that the things you have to prove or not prove, if you compare to people doing it more like set theory in homotopy type theory, where they actually force the Hom sets to be sets by truncating, you just move the proof obligations around. And so what happens is in setoid-based category theory, it's kind of like 1.2 instead of like one category theory or two. It's like there's a little bit of the two stuff that trickles down a little bit early, but that's it. And since we were going to do bi-category theory anyways, it didn't hurt.
Thank you. Interesting that you were able to find insights in category theory based on this attempt to encode things in type theory. So I guess this proves that type theory is really good friends of category theory, perhaps better than set theory, although this may be a controversial statement.
If you choose the right definitions, then category theory can fit very, very well. But and there's no new ideas, but you do have to pick. There already exists, but it's not open any textbook.
So every other question should be asked in the breakout room now. I'll actually move to the breakout room in 20 seconds myself because I have a question. For this session, I'll hand over to Amin yet and now, and want to thank the speakers and all the people asking questions again. Thank you. Have fun in the next session.
Excellent. Thank you very much. So Amin, I assume you are here, so I have promoted you to co-host. But before that, I think Katalin would like to insert a really small comment on the next paper. Katalin?
Yes, I thought we were doing it after the talk, but
oh, right. Oh, that's fine.
We can also do it now, no problem. Let me share screen. Present. Oh, I need to do them in the other order, which is also fine. So yes, can you see my screen? This is one of the distinguished paper awards. We've introduced this starting this edition, and we were wondering what the best way would be to award something over the internet. So this is what we came up with.
Katalin, low volume, please. Low volume when you play it. Sorry. Not now, but when you play it.
I don't know. It doesn't even play. There was supposed to be clapping sounds, but it doesn't seem to work.
I'll print the certificate and hang it on my wall.
Okay, so I'll
Thanks very much.
Give it a rub.
My talk was pre-recorded.
Yes, I'm just starting it. Give me a second.
Okay, cool. Thanks. I'm Rob Lewis. The work I'm presenting is joint work with Johan Kamelin. To give a quick overview of our project, we've formalized in Lean some of the theory behind Witt vectors. Witt vectors are a mathematical gadget that's used in modern algebraic number theory. Specifically, we've constructed in Lean the type of p-typical Witt vectors. We've defined its ring structure, and we've proved that the ring of Witt vectors over the finite ring Z mod p is isomorphic to the p-adic integers. This talk is too short to go into any real detail. So my plan is to explain why this is an achievement and to show a particular proof technique that we used. And then my co-author Johan will go into more detail in the longer talk. So why is this an achievement? Witt vectors are a notoriously difficult mathematical thing to master. There are a lot of details that are folded into the construction at the very beginning. And then later on, when you're trying to prove things about them, it's completely intractable to actually look at these details. Essentially, you have to enforce an abstraction barrier. You have to follow higher level strategies for your proofs. And the justifications for why these higher level strategies actually work, well, they really take some mathematical maturity to understand. So this sounds very hard to formalize. Proof assistants don't have a sense of mathematical smell. They don't know when you're doing something wrong. So we need some new techniques. What we've done is isolate the key mathematical insights that really justify the strategies for computing with Witt vectors, which are really not spelled out in the literature. And we've wrapped these insights in little bits of metacode that allow us to simulate the informal reasoning patterns in Lean. As was put by one mathematician who's familiar with the frustrating details of dealing with Witt vectors, we've tamed the beast, so to speak. So the underlying data of a Witt vector is actually very simple. We're going to fix a ring R and a prime number P that we'll use in a second. A P-typical Witt vector is just an infinite sequence of elements of R. Traditionally, we write it from right to left. The complexity of this definition comes when we define the ring operations on this type. They're not component-wise. And we're going to look at addition as an example. The nth component of the sum of x and y is a polynomial function, let's look at S2, applied to the 0 through nth components of x and the 0 through nth components of y. And these polynomials, S2, S1, etc., these depend on the prime number P. So in a 10-minute talk, I'm not going to go into more detail here. Suffice it to say that the details of this construction are pretty intricate. We want to avoid thinking about this as much as possible. So we're all familiar with formalizations. When you define a new kind of object, you need to say what you can do with that object, and you need to prove a bunch of lemmas about how the different operations interact. So there are a bunch of functions that go into the basic Witt vector API. Again, I'm not going to go into detail about any of these. I just want to point out the ghost map W at the bottom here, which maps a Witt vector into an R sequence, a sequence from the natural numbers to R, which is also a ring that has the more familiar component-wise ring structure. In general, this map is not injective. And this is going to appear when we talk about our strategies. The challenge is, how do we prove properties of these operations without actually looking too hard at the definition of the ring structure? And there are two strategies that appear in the literature that we've kind of synthesized here. The first strategy builds some scaffolding. You step up through levels of complexity of the ring R that you're working over. This works, but it's tedious. Strategy 2 is faster, it's freewheeling, but it sounds, at least as we've presented it here, it sounds unsound. Why should this actually work? Well, so here's some mathematical maturity comes up again. If you're trained in this area, these two strategies are basically the same thing. You can justify strategy 2 by noticing that it's a reformulation of strategy 1, and strategy 1 obviously works, so you're good. But the details of actually carrying out these strategies are very different. And if you can't recognize the similarity here, you're stuck with the slow, fumbly one. We'd like to use the second one as much as possible, but it sounds really hard to formalize. And in fact, in Hazelwinkel's presentation of Witt vectors, he warns of pitfalls when you're using this strategy. If you don't restrict yourself to something called uniform calculation, or universal calculations rather, you're going to run into trouble. So you'd better know when you are dealing with only universal calculations. So our insight is that by universal calculations, essentially what we mean are calculations that are done on polynomial functions. The notation I use here is a little more explicit than we'd see in informal literature. Normally, the dependency of this function f on R wouldn't be noted. We just talk about f. But this really obscures what's going on. So we say that a function f is polynomial if there's a family of polynomials phi, such that for every ring, if we look at fr, and if we look at the nth component of fr, this is given by the nth polynomial phi applied to the coefficients of the input x. The quantifier order here is important. Phi does not depend on the ring R. And this definition is key because of its extensionality rule. If we want to show that two polynomial functions are equal, then it suffices to, first of all, work over the integers instead of our original ring R. And then we can just apply the ghost map to both sides. And remember that the ghost map moves us into the familiar ring structure R to the n. So these calculations are really much more tractable. You should also note that morally, we can think of some generic ring in place of the integers. If we prove this for some ring that we know nothing about, then we can obviously specialize that to the case of the integers. Okay, so with this definition, this theorem in mind, we can reformulate our strategy 2, show that both sides of our identity are polynomial functions, and then use extensionality to reduce this to a computation on ghost components. So this is great. Not only are ghost component calculations easy for us to do, they're in a convenient ring, but showing that things are polynomial is actually pretty simple too. Essentially, we're going to have to prove one lemma after defining each of our API functions that says this thing alone is polynomial, and then compositions are all handled completely automatically. So with some fairly simple metaprogramming that we describe in our paper, we can actually make this strategy look exactly like it would look on paper. So this example is one of many similar identity proofs that show up in our formalization. And we simulate the strategy of ignore that the ghost map isn't injective, apply it anyway. We're going to step through the tactic state in these first 2 stages. So notice that here, we're working over some ring R. After I apply the tactic ghost calc, we see that we've taken the ghost component of each side. If we're able to prove the original goal, if we can prove for each n that the nth ghost component applied to the left-hand side is equal to the nth ghost component applied to the right-hand side. Under the hood, if you look at that extensionality theorem, it's actually the case that this ring R has changed. This is not the same ring R that it was before. But the only hint that it's changed is that the name of this instance, its commutative ring instance, has changed. Otherwise, it looks exactly the same. And then after this point, we can do a simple induction and then simplify. This goal over computing with ghost components is provable by standard rewriting. And this pattern shows up again and again. For all of these identity proofs, we apply the ghost map, we do minimal or no preprocessing, and then we call the simplifier. So this works in practice. We built enough of the Witt vector API, proved enough of these relations to prove a fundamental theorem about them. This is not the focus of the talk, so I'm going to leave the details here again for Johan. The main takeaway message for this short talk, to me, is that with the right idioms, we can formalize mathematically mature topics. And furthermore, that trying to formalize these things can bring these right idioms to the surface. They're obscured in informal presentations, but formalizing makes us really think about them. Our project is not huge, and some pretty elementary metaprogramming helps a ton, not only to keep things short, but also to keep things what we consider very mathematically legible. So thank you very much for your time.
All right, thanks, Rob. We have Rob here.
I'm here. Yep.
So if there are questions, please raise your hand. Do we have any questions? Okay.
I see a raised hand in the video.
Yeah, Andre.
Right. So I have a quick question about your extensionality theorem. It's essentially a transport theorem, right? So in some sense, any universally quantified equality between 2 polynomial functions is transported across this theorem, if I understand correctly. Can this be generalized somehow? Can you have statements of a more complex combinatorial nature that have this nice property?
So I'm not completely sure what you have in mind, but my guess is no. I mean, I think it's a relatively subtle, and it's a relatively specific kind of theorem. What you can generalize is the arity of the functions that you're working over. So I think we have examples in our paper of polynomial functions of arity 0, 1, and 2. It works for n-array functions. I mean, in our development, you don't see anything of higher arity, and you rarely come across these things, so it's not worth that generalization.
I see. Thank you.
Hey, if I may ask one question. In what you showed, you had this metacode, ghost calc, right? Do you prove that it always works, or is it some tactic that you apply and then you see if it gives a result? It's a tactic, so.
There's nothing verified about the tactic itself, but it's really doing very little. All the ghost calc tactic does is infer that both sides of the equality are polynomial functions. And then
okay, I see. Okay, thanks. Yeah, I guess we can go to the next talk. And for people who want to discuss this further, there's the break room.
Okay, I'll move over to the breakout room. Thanks very much.
Yep. Thank you. So the next talk is on formalizing, on formal verification of semi-algebraic sets and real analytic functions. Is going to be presented by Tanner Slagle. I guess that's the recorded talk. Yeah.
Hey everyone, thanks for tuning in. My name is Tanner Slagle. I'm a civil servant at NASA Langley in the Formal Methods group. I'm going to talk to you all today about a formal verification of semi-algebraic sets and real analytic functions that me and a couple colleagues did in PVS, which is the interactive theorem prover of choice in this office, at least. So let's talk about motivation for this formal verification. In the Formal Methods group here, we want to be able to reason about hybrid systems. So hybrid systems are dynamical systems that have both discrete and continuous variables in time. So a hybrid system often has a safety critical component. Perhaps it is a human life or some life, or perhaps it's a lot of money on the line. So you really want to be able to formally verify safety properties of this hybrid system. One way to do that is with differential dynamic logic. It is a logical framework that you can reason about hybrid systems. So the overall goal here is to implement DDL in PVS. The issue is that to implement DDL in PVS, it requires a lot of theory of ordinary differential equations, as well as the focus of this talk today, which is multivariate polynomials, semi-algebraic sets, and real analytic functions. A little example in the diagram to the left here. Imagine this as an aircraft, and the aircraft path is a solution to a differential equation. We're going to assume that that's real analytic. And then it is navigating through a geofence, which is the blue line. So a basic property we might want to prove here is that when the aircraft leaves the geofence, it will leave for a complete interval of time. So you can see at the bottom of this blue semi-algebraic set, the path of the aircraft totally leaves the semi-algebraic set for a full interval of time. This is something that I think we would believe about an aircraft, but proving it in terms of real analytic functions and semi-algebraic sets actually takes a little bit of work. But being able to prove that sort of validates using these sorts of mathematical objects as a model for aircrafts and geofences, etc. So here's the way the outline of the rest of the talk is. This is the short version of the talk. I'm going to quickly talk about the formalization we did of semi-algebraic sets to real analytic functions. And I'm going to spend a little bit more time talking about the real analytic function behaves on the boundary of a semi-algebraic set, like I described in the last slide. So when we formalized multivariate polynomials in PVS, the way we did this was we started with a monomial, and we defined it as a record data type. And then a multivariate polynomial would be a list of these monomials. So you might imagine that if you have a list of monomials, there are many examples of syntactically different multivariate polynomials that are actually the same in terms of evaluation. So one big hurdle we had to deal with was developing something called standard form. You'll see an MV standard form here, MV standard form. And we had to show that the standard form of a multivariate polynomial was unique. And that's what this PVS theorem is showing right here. It's saying that if two polynomials have the same standard form, that means that they evaluate to the same value for every single choice of inputs. All right, so once we have multivariate polynomials in PVS, we can go on and define semi-algebraic sets. An atomic polynomial formula is a record type in PVS, and it has a polynomial and an inequality. The way that a vector satisfies an atomic polynomial formula is you evaluate the polynomial at that vector and use the inequality to compare it to 0. If you get true, then that vector satisfies the atomic polynomial formula. So once you have atomic polynomial formulas, we can make a quantifier-free polynomial formula. We chose to define a quantifier-free polynomial formula in disjunctive normal form in PVS. What this means is that it is a disjunction of conjunctions of atomic polynomial formulas. So a conjunction of atomic polynomial formulas is called a meeting, it's a list, and a disjunction of those conjunctions is a joining, and it is a list of meetings. Once you have a quantifier-free polynomial formula, you can define a semi-algebraic set as nothing more than the set of vectors that satisfy the quantifier-free polynomial formula. Okay, so you've probably heard of analytic functions in the complex analysis world. The real analytic definition is very similar, but it is equivalent to a lot less powerful things. So a function, a real valued function, is real analytic at a point, means that that function in some neighborhood around the point equals some power series. In PVS, we showed the sum of two analytic functions is analytic, a constant multiple of an analytic function is analytic, the product is analytic, and a non-negative power of an analytic function is analytic. And all this was enough for us to really get to the meat and potatoes of what we were trying to prove. This is one of two of the main theorems, and this one I call the clean exit theorem. And it is categorizing the exact way a semi-algebraic set or a real analytic function might leave a semi-algebraic set. Basically, one of these three cases happen. The first case is that the function never leaves. It stays in the semi-algebraic set for all moments of time after you start paying attention. The second case is that there is a point where the function is outside of the semi-algebraic set, and the very first point that it exits the semi-algebraic set, it exits just for that point, and then is entirely inside the semi-algebraic set for some amount of time completely. This is basically a function coming up to the boundary of a semi-algebraic set and bouncing back in. The third case is truly a clean exit. The function goes to the boundary of a semi-algebraic set, and then it leaves for an entire amount of time. So you see that f of x star plus t is totally on the outside of the semi-algebraic set for an interval of time. If we look at this graphically, this graphic is showing case 3. We have this real analytic function, and it leaves the semi-algebraic set for an entire amount of time. The second case would look a little different. The real analytic function would come to the boundary of the SA set, which is not in the SA set. It can be, but in this example, it is not. And it would bounce back inside the semi-algebraic set. So it would just exit the semi-algebraic set for a particular instance. So this is a pretty basic property. If you take time to think about it, this is a basic property. And you might wonder if real analytic is a bit of a too strong of an assumption. So it's worth noting when you relax the assumption of real analytic to smooth, which means infinitely differentiable, you do not have this clean exit property. This is what it looks like in PVS, but I'm going to describe it with this picture. You have a semi-algebraic set defined as this bottom half of the plane. And this SM function is smooth, but not real analytic at 0. So this SM function is in the semi-algebraic set all the way to 0. But then for any neighborhood of time you take after 0, any positive amount of time after 0, there are infinitely many points that are inside the semi-algebraic set and outside the semi-algebraic set. In particular, if you look at these peaks of the function, every one of these high peaks is outside of the semi-algebraic set, and every single one of these low peaks is in the semi-algebraic set. Therefore, SM does not leave the semi-algebraic set fully for any complete amount of time, and it also doesn't satisfy either of the other two cases. So smooth is not quite strong enough of an assumption, but real analytic is. Well, I hope I did this in 10 minutes. Let me wrap it up a little. I've talked about a formalization we carried out in PVS. I went through it very quickly. If you want to look at the details, check out the longer video on YouTube. Some future work we could do, really I'll skip to the most important one. We need to develop the theory of differential equations in PVS more. In particular, we have the way a real analytic function behaves with a semi-algebraic set, but we need to know when is the solution of an ODE real analytic, and that theory exists in the world. It's just a little piece of the puzzle that we need to implement into PVS. I want to thank the organizers of this conference. You all have done an awesome job. I want to thank you all for listening, and I'm sure wherever I am right now, I'm ready to take some questions and hear your thoughts. So thank you very much for listening, everyone.
All right, thanks. We have some time for questions or comments. Yeah. Yes, Andrew?
I think it's really nice that you are implementing differential dynamic logic in PVS in a certified manner, and you're basically proving all the theorem infrastructure for that. But yeah. I guess that the implementation could proceed largely independently of this certification aspect, right? So has implementation work already started, and how does it really come together with your formalization?
Oh, that's a great question. So we have the implementation of DDL is currently in PVS. We wrote it so that I think it is functional now, but a couple of the rules of DDL are written as axioms instead of lemmas. And then the goal is, as we build up the mathematical theory and everything necessary, we'll be able to actually prove those instead of assuming them. So right now, I think there are just 2 axioms left. And hopefully this project will get rid of one of them in the next month or 2.
I see. Best of luck with that.
Thank you.
Okay, any other questions or comments? No, okay. Then I will ask a question. You mentioned that you need this uniqueness of representation of polynomials, but you didn't say where this shows up, and it apparently is a lot of effort to prove this.
Yeah, so it did take work to prove the uniqueness. I'm not actually sure if in the development of semi-algebraic sets, we require, okay, when we define semi-algebraic sets, we do require that the polynomial used in the atomic polynomial formula is in standard form. So it's required for our definition. I don't know if there's any practical reason why we enforce standard form. We thought of it as sort of a fundamental property for multivariate polynomials, so we included it in the formalization. But offhand, I can't think of a exact reason why we require it in the definition of semi-algebraic sets. That's a good question. I'll have to think about that some.
Okay, thanks. Anyone else? We have 1 minute. Otherwise, I guess we can start the next talk. Right, so the next talk is on the formalization of Kolmogorov complexity. And Elliot Cutt is going to present.
I'm going to talk about the formalization of Kolmogorov complexity in whole. This is some work done by Elliot Cutt and Michael Norrish from the Australian National University, Data 61 and CSIRO. So overview of the work we did, and you can find the full details in the.
Andre, is something wrong or?
What's going on? Leonard?
You're muted.
Sorry, I may have shared the wrong screen. Give me
No
a second.
problem.
I can do it otherwise, but it might take a little bit. But if it's
Just let us know. I can also do it. Looks good.
Today, I'm going to talk about the formalization of Kolmogorov complexity in whole. This is work done by Elliot, Cat and Michael Norrish from the Australian National University, Data 61 and CSIRO. Okay. So overview of the work we did, and you can find the full details in the paper. We carried out a whole mechanization of Kolmogorov complexity, and this involves defining Kolmogorov complexity, proving Kolmogorov-Crafts inequality and the Crafts inequality, proving the invariance theorem for Kolmogorov complexity, the incomputability of Kolmogorov complexity, and some various inequalities about Kolmogorov complexity. But what is Kolmogorov complexity? The complexity of a string, we say, is the size of the smallest machine or program that produces it. So something like the first million or billion digits of pi would not have a very high Kolmogorov complexity because we have programs which can produce these, the first million digits, very short programs which can do this. Truly random strings have high Kolmogorov complexity, where the best program that can produce that is effectively the program which contains the string itself. But what do we mean formally by Kolmogorov complexity? So we say the smallest machine, we let this be some universal machine. Then we say the Kolmogorov complexity of x for this machine U is this minimum length of p, where p is run on this machine U and it outputs x. But U may not be universal. We define this generally, and if there is no program which can produce this x, then we just return none. So this U takes just one parameter, the program, whereas the phi, the general universal recursive function, would take two, the index and the input. If U is universal, then this program is the encoding of the two arguments that phi would take. But what is this P we're talking about? So you can describe it as numbers, which is what you would normally do with recursive functions, but we'll describe ours as a list of bits or a Boolean list, and there's a bijection between the two of these that we will use. We won't describe it here in the talk though. And this bar over P is just the length of this list. Without getting into the hairy details, one of the things we can prove about Kolmogorov complexity is this invariance theorem, which more or less says that it doesn't really matter which machine you're using, that the difference between the Kolmogorov complexity of two different machines is at most a constant that does not depend on x. So this inequality is true for all x. There's a fixed C in which this is true for all x, where U is some universal machine and M is just some other machine. May not be universal, just some other machine. Another topic that we covered in our paper was prefix-free sets. Just briefly, a set is prefix-free if for any pair, S1, S2, neither S1 is not a prefix of S2 and S2 is not a prefix of S1. So this set here is prefix free because none of these are prefixes of another, but this set is not prefix free because 1, 1 is a prefix of 1, 1, 0. And why are we using prefix free sets? Well, there's this kind of neat inequality about them that if S is a prefix free set, then summing over the elements of S 2 to the minus the length of those elements is less than or equal to 1. Kind of neat. And there's a inverse, which we also proved is if this inequality is satisfied, then there is a corresponding prefix free set where the elements match the lengths of the elements of this. And how does that relate to Kolmogorov inequality? Well, we can define a machine, a prefix free universal machine, then we can use that to give us a prefix free set and effectively just apply the Kraft's inequality over that, and we get this neat fact about Kolmogorov inequality with respect to this specific prefix free machine. The final result that we're going to talk about today for Kolmogorov complexity is that it is not computable. There's no recursive function which can compute this. It was slightly difficult to find a careful proof for this. It ended up using some weird arithmetic about natural number logarithms. This was mostly because we were talking about the length of strings, and then this length of a binary string is in the number form, similar to a logarithm. But it is interesting that it did not depend on using Turing machines. In fact, we used lambda calculus and recursive functions for our proof. But we did have to have this index of computable functions. Okay. So lambda calculus really was at the core for all this work for the computability theory side, even though Kolmogorov complexity is often described using Turing machines and tapes and things like this. We're able to use lambda calculus to define and solve or prove these theorems. The invariance theorem was a neat result. The Kolmogorov inequality was really more a fact about prefix-free sets. The Kolmogorov aspect of it was not too difficult. The incomputability, once we found a good proof in the literature, we're able to prove that nicely. And one thing which we didn't touch on in this talk, but you can find in the paper, is some various Kolmogorov inequalities that are rather interesting, and some of them quite difficult to prove. So future directions, things that we might work on, theory of recursive degrees. We could use this to show where Kolmogorov complexity is in the arithmetic hierarchy, which would be interesting. The undercidability results relating to that. Classical complexity theory, so like O of n and O of log of n and these kind of things. This might be hard, with the lambda calculus. So we might have to use the formalization of Turing machines for that. And another thing which relates to Kolmogorov complexity is Solomonov's induction theorem and the intelligent agent IC. So there's just some other things we could work on. Thank you for coming to this talk.
Okay, let's get started.
All right, thanks. I guess we have plenty of time for questions. There is any questions? Okay, let me start by asking, I guess, who is present here? Actually, I don't see. Okay, Elliot is here. Yeah, okay, good. Let me start by asking, you said that you're using lambda calculus instead of Turing machines. So I'm curious, was it because working with Turing machines was particularly uncomfortable, or working with lambda calculus was very nice? Or...
Yeah, I kind of expected this question. Yeah, so a lot of what we had to do was basically implement programs of things. So like, for instance, a print program or a concatenation program or something. And describing these with Turing machines is a little bit of a pain, but for lambda calculus, and it was definitely much easier, I would say. Yeah.
Right. And did you have to?
Okay, go ahead.
Go on. Did you have to then convert between the two, prove an equivalence and expressivity and things like that?
So there was a previous work by Michael on proving that, implementing lambda calculus and then showing the equivalence to recursive functions. Whole 4 doesn't currently have Turing machines implemented in it. I think it's still underway, but there is this computability for recursive functions lambda calculus that's already there. Yeah. So we didn't use Turing. We didn't convert back to Turing machines at all. We just talked about these these machines being objects over these strings. Yeah.
Can I join in on the question?
I think so, Andre, the question, but yeah, go on.
So imagine you now have a nice theory of Turing machines or mu recursive functions in Whole 4. How abstract are your proofs at the moment? Can you easily switch models of computations, or would it actually be redoing everything again?
Oh, that's a really good point. I think most of our proofs are pretty abstract, I would say. There's like a few core results, like core things we'd have to change. I don't think it would be too bad. Yeah. Yeah. Basically, if you could describe doing some basic things over strings, like some basic operations over strings, then you could recover the proofs pretty quickly, I think.
And the arithmetic also does not depend on the model, so it's really on another level.
Yeah, yeah. Oh.
Cool.
Right. Any other questions, comments?
Yeah, just a comment here. It seems that this lambda calculus versus Turing machines is one of the more debatable aspects. So you mentioned that when switching to complexity, you want to give up to the lambda calculus ideal and switch to Turing machines. I think this would be a defeat, right? You should stick to some form of an instrumented lambda calculus.
Yeah, I mean, we have implemented sort of step measuring function, and we could, I guess, do it with lambda calculus. But I think it's just the fact that most of the literature on these complexity measures, I mean, maybe I just haven't found it, but I don't know if there's too much literature on these complexity textbooks and stuff where they use lambda calculus instead of Turing machines, right? Like you'd have to kind of reconstruct these things yourself and then also implement them. So yeah.
See, thank you.
Hey, we have a couple more minutes. Yannick,
I have another question.
Yeah, go on.
So in the incomputability proof, you mentioned you had to recover lots of details. And I read the Wikipedia article of Kolmogorov complexity a while ago, and compared to other undecidability proofs, it's really a detailed proof. It really goes into the details. If you read the proof for, I don't know, Rice's theorem, you cannot really recover a formal proof from this. You have to do it yourself. But here, textbooks go into detail. Can you elaborate a bit more on the details you had to come up with for your proof?
So we kind of based it on a proof from Hutter's Universal Artificial Intelligence book, where he, the start of the book, he talks a lot about Kolmogorov complexity, and he has this really nice proof. And I mean, if you watch the long presentation, we go over the incomputability proof pretty simply. But I guess the things we had to come up with were, let me think, were it didn't, the versions of this proof in the go-to Kolmogorov complexity book, like Liam Vitani, they didn't really cover it too formally. Yeah. So we kind of had to find the one which was really nice, which was the Hutter book, and then use that one, I guess. Yeah, but if you watch a long presentation, you can see the proof, and I don't think it's too complex in that presentation or in the paper. Yeah.
Okay, it's about time. If there are no other comments, I think we can thank Elliot again.
Yeah, and
right, and
we can still do the breakout room thing, although I didn't see that many people in the previous breakout rooms, unfortunately. So maybe just a few announcements. We're taking a break for 30 minutes, and then we are having the virtual conference dinner also on Zoom, on a different Zoom. So join us in 30 minutes or join the breakout session here. Thank you.
One quick question, Katalin. Is the Clouder webpage working for you?
The Clouder webpage is working for me. I've heard that there are people having troubles though. And that what helps is clearing all data that this website stores locally.
Okay.
In the browser.
Yeah, sure. I'll give it a try.
I mean, it's not perfect. The message, the delay between the messages.
Oh, I don't see anything anymore.
I guess you might have to also re-log in and things like this. By the way, we should stop, recording and live streaming.